Mr. Gunpinar is, as you see, that Istanbul Technical University. He was a master student here 13 years ago, 14 years ago. He got his PhD from Tokyo University. Oh, he worked in Samsung.
Yes.
Heavy
industries, yes.
Industry, and then moved to got PhD, and now he's in Istanbul. Okay, go ahead.
Okay, thank you. Thank you for the introduction. So I'm glad to present our research topics here through Zoom. So I'd like to ask you, first of all, how many of you heard about generative design? Okay, some of you heard about generative design. So actually, it's an open issue right now. So in the CAD community, so we have focused on this research for about 3 years. So before explaining generative design and its applications in CAD, I'm going to shortly explain my university and our school. So actually, it's Prideaux University, which was established in 1773 as Imperial School of Naval Engineering. So it gets his name in 1944. So right now we name this university as Istanbul Technical University. We have several campuses, and it's one of the biggest technical university in Turkey. So actually, mechanical engineering department here in ITU, we shortly call it ITU, is one of the best mechanical engineering department in Turkey. So additionally, actually we have a good location. Professor Han already visited our faculty. He was here about 2 weeks. So maybe you know Turkey connects Europe to Asia. So this side, on the right side you see an image. This side is Europe, and on the other side you see there is a Bosporus here, there is a sea here. On the other side you can see the Asia. So our faculty is located in a very good position. So this is the view just in front of our university. So you can see here a soccer stadium. So maybe you see a European Champions League, soccer league. So this is the stadium for Beşiktaş soccer club. So maybe you can see their soccer in European Champions League. So the next you can see our laboratory. So actually we name is at SmartCAD. It's very similar to iCAD, right? Intelligent CAD Lab. So that's why I was inspired from. So I named it as SmartCAD Laboratory. So we focus on the development of geometrical tools, geometrical modeling methods and algorithms. So we do smart product design, and then we develop high-level CAD tools and so on. We also focus on generative design. So before giving descriptions about generative design, let me talk about me and myself and Korea. So actually, I lived in Korea for 7 years. I was a student between 2004 and 2006. I was a member of iCAD laboratory, which is led by Professor Han. So my thesis title when I was in iCAD lab is interfacing heterogeneous product development management systems using the PLM services. After that, I started working as a research engineer in Samsung Heavy Industry in Mechatronics Center. Actually, Samsung Heavy Industries is located in Koca Island. It's on the south side, but I was in Tejon in the Mechatronics Research Center. So this is the contents of our research about generative design. After shortly introducing you generative design, I will explain a GD algorithm. I will shortly call it GD algorithm. And then I will talk about two applications, one for yacht hulls, another for car side silhouettes. So finally, I will conclude my talk. So actually, the typical approach in design is there are designers, and designer tries to obtain a design based on some criteria. But in generative design, the computer generates new designs or models without a user. Okay, there is no user here. So you make computers to involve the design process. So we have a generative model, which is a mathematical model manageable by the computer. You see here on the left side, there are some mathematical formulas here on the left side. You put them in a computer, and finally, you can generate these shapes, okay? So there is no user here. The computer automatically generates without human intervention. So the question here is why we use generative design. First of all, human may not and also cannot always anticipate or generate all design options. So when you see here on the right bottom, let's say the red boundary is our design space boundary. So in this design space, we have infinite number of design options. So what a designer's attitude is like this. He starts with a design. Let's say the blue dot is a design. He designed this one. He starts with D1, and then he simulates and he performs some computer-aided engineering simulations, and then he says, let's modify this design, and then he gets another one, D2. And then finally, he gets D3, D4, and the design D5. And then he converges to D5, to design D5. So D5 is the final design, actually. So you see, most of the portions in the design space are not covered and are not scanned by the designer. Okay, this is the biggest problem in traditional design approach. Therefore, we think that computers can scan infinite design options, some of which may not be considered by humans. Okay, so on the left side, you will see the traditional design approach. What a designer does is he designs. Okay, he designs first, and then he validates through computer-aided engineering applications, and he can get feedback from these applications, and then he modifies his design, compacts here, designs again, validates, designs again, validates. So there is some iterative approach here. And then he converges a design. Okay, it's a typical approach. So we want computers to do this design process instead of making designers to do this. So we believe that in such approach, we can scan all, not all, but many design options in the design space. So there are some GD projects and systems in literature and in the market, in the computer design market. The first one is Autodesk project Fractal. Another one is Rhino Grasshopper, and the final one is SolidWorks Genoform plugin. So in the bottom, you can see Genoform plugin. So what you do is you don't need to do anything else. You can just score it. So the system shows you some designs. You score it here, and then on the left side, you can see the score. And then finally, the system automatically generates new designs for you. So these are the steps for generative design. So it involves three main steps: model parameterization, so design space setting and design generation. So I'm going to explain all these steps one by one in the following slides. So parameterization means actually before starting the design, the designer creates the CAD model, and then important design parameters here are determined and tagged. So you see here on the left side, there is a cup. Here is a cup. So we parameterize this wine glass using design parameters. For example, here we have one Bezier curve here, cubic Bezier here for the bottom part. For the top part, we have another Bezier here. So these are alpha 0, alpha 1, alpha 2, alpha 3. These are the design parameters. These are the coordinates. Once you change these coordinates, you can generate new designs. Okay. So, so a CAD model here for a wine class with its design parameters. So on the right side, you can see a CAD model for a yacht hull with its design parameters. Okay. So in case of yacht model, we have entrance length here, and then we have middle length, we have aft length. Here we have an angle, entrance angle. We have depth here for the entrance section, middle section, and aft section. So first of all, you should define your parameter. You should define your CAD model using parameters. Okay, this is the parameterization step before using generative design algorithms. So the next step is to set the design space. So you can think design space as a box. Okay, if you have just two parameters, you have a rectangular space. You have just two dimensions. If you have three parameters, design parameters, for example, length, width, and height, so you have three-dimensional space. So what you should do is you should set your design space. So how you set this? You should first of all determine the parameter ranges so that you can define a box as a design space. And the next one is you should determine and quantize the design specifications. So these are served as geometric constraints. So you can say these are defined in advance before starting your design. For example, if you want to design a car, so you should at least know about its length. If you design a yacht hull, so the user or the customer gives you a design specification. He wants you to make it, for example, 1.5 meters high. Okay, these are already defined before starting generative design. So once you define your design space and once you parameterize your model, you should select the generative design algorithm for your applications or propose a new GD algorithm specifically for your program. So you can see here on the bottom, everybody. So here it's a ceramic structure. So all of these are generated using generative design technique. So what you should do is you should use a GD algorithm. Okay. So this is the motivation for generative design. Once again, using generative design, you can generate new designs without designer. So computer generates design or synthesize designs instead of designers. Okay. So next, I will explain a GD algorithm. So this is proposed by our group and published in Computer Design and Graphical Models journals. So, so we should first of all parameterize the model. So let's define some important notations here. So a shape or a design is represented using n-dimensional design coordinates. So we have x1, x2, and xn. Each of these parameters represents a design parameter. So design space here is each coordinate here, x1, x2, and xn, represents an axis in the design space. So for example, if we have a length, if we have a design parameter which is length for a yacht hull, this length parameter represents a dimension, or we can say represents an axis in the design space. So if we have, for example, n dimension or n design parameters, we have n-dimensional design space. So actually, generative design is a high dimensional problem. So here we should also set lower and upper bounds for the design parameters x1, x2, and xn. So this will set the design space boundary. And then finally, we should set the design constraints. These design constraints classify the designs into feasible and infeasible ones. In the bottom, you can see a design space with red boundary. So actually, I'm visualizing using 2 dimensions. So we have this is, let's say, a two-dimensional space. We have just 2 parameters. One axis here represents the x1, another axis represents the x2 dimension. So the gray ones are the infeasible design space. So we want to generate designs on the white regions. Okay, if you generate a design inside the gray region, it's an infeasible design. So here is algorithm flow. So we have 2 or 3 steps here. The first one is particle insertion, and the other one is particle tracing algorithms. They are executed iteratively until reaching the user-defined execution time. And then here, the particle position. So actually, we have a design space. We place particles in the design space, and particles position represents a shape or a design in the design space. So here we have, let's say, design space. So we have a particle here. I'm not sure you can see my mouse. Can you see my mouse?
Yes.
Yeah, you can see my mouse. For example, if you locate or position a particle here, so the location here represents a design, a shape in the design space. In particle tracing algorithm, we move the particles in order to obtain feasible shapes. Once we iteratively execute these 2 algorithms, finally we have lots of shapes, for example, 1,000 shapes, but we cannot get the 1,000 shapes, so we should select the representative ones. We can select 10 representative shapes by using clustering algorithms. So I will explain the steps one by one. So the first step is the particle insertion. So this, let's say we have a 2-dimensional space here, x1 and x2 here. Actually, this is n-dimensional problem, but I should simplify it in order to make you understand the generative design problems. So let's say I have 2-dimension here. I have a 2-dimensional space, 2-dimensional design space. You see its boundary in red. So each dots here represents a shape in the design space. So in the particle insertion algorithm, we are gonna insert particles. And for example, we will insert 10 particles at the same time. We can insert the particles randomly, but this is not preferable. So if you insert randomly, for example, here in this case, we have particles just on the diagonal, but you don't have particles here on the left top or right bottom. You cannot see particles. If you cannot insert the particles here, you cannot generate shapes here on this portion and also on this portion as well. So this is called as non-space filling. So in the particle insertion step, we want space filling particles. So we use Alzheimer's potential energy, so which is based on analogy of minimizing forces between charged particles. So on the right side, on the right image, you can see space filling particles. You see that particles have some uniform distance between each other. So here we simply use some formula. This formula favors and positions the particles to the positions so that they distributed uniformly. Okay. So this is the first part. This is the particle insertion step. Once we insert the particles, we should move these particles in the design space in order to obtain desirable shapes. For example, this is my design space or shape space, and this is my particle. So we can move this particle. In case of 2-dimensional space, we can move, we have 4 options. I can go on the right side, left side, top or bottom. So we move the particles based on a cost function. We have a cost. This cost is based on the design constraint, which has been already defined by the designer. So for example, I have here 4 directions. I go in this way, because in this way the cost is minimized more. The cost is minimized more. So we can move the particles in this manner, and then we should of course stop the particles at the end. So we have several rules here. We have 5 rules here, but I'm gonna just emphasize the final rule, reaching the shape space boundary. When you see the image E, the particle starts from this location and go this way, and final stops when it reaches the shape boundary. So once we obtain, so let's say we inserted 10 particles, and 10 particles terminates at the end of applying a particle tracing algorithm. So once we have 10 positions or 10 shapes at the end, so once we have 10 shapes here, we iterate once again. So we iteratively apply particle insertion and particle tracing steps, and at the end we have, for example, 1,000 shapes. So among those 1,000 shapes, we should get, for example, 10 of them. So here we use clustering algorithm. This is based on K-methods. So by using this algorithm, we can select the representative designs. So once you apply these algorithms consecutively, so you can generate shapes. So for example, this is wheel rim. This is wheel rim. So in the wheel rim design space, these designs are somewhat most distinct from each other. They are different from each other. So based on this formula, this energy minimization formula, we generate these designs. This is for wheel rim. So you can see here the examples for wine glass. So you can see very interesting shapes here. Some of them may not be producible, but if you include the manufacturability constraint here, you cannot get some infeasible shapes. This is everybody. So these shapes are generated by our algorithm. So this is yacht holes. Once again, there is no user here. So if you want to check the more details, you can refer these papers, these 2 papers which were published in this year, 2018. Okay, next one is, I'm going to explain you 2 application scenarios for generative design. The first one is for yacht holes. So here what we did was we introduced adjective-based design concept in yacht hole design. So you may hear for the first time. So in adjective-based design, we express holes with adjectives such as strong, speedy, and aesthetic. So let's say you have one model, you have a model, a design model, a CAD model. So you want to make it to be to look like strong. So what you should do is you should use our adjective-based whole design framework, and then you can automatically generate strong model. Okay. Otherwise, you should strive for the generation of strong holes, which may take about more than an hour, 1 hour or 2 hours. I don't know. So here in this research, to make this adjective-based design concept available in yacht hole design, we developed 2 systems. The first one is a parametric hole design framework. Another one is an adjective-based hole design framework. So once again, the first step for generative design is you should parameterize your CAD model. So what we do is, this is a yacht hole. Please neglect the top side. Just focus on the bottom one. This is a yacht hole. We parameterize it using Bezier curves. So here we have 3 sections: entrance, middle body, and run section. If we get the sectional wave here between middle body and run section, you can see its appearance. So we have one depth parameter here, we have width parameter here, and we have many more parameters here. Similarly, we have length here, we have entrance angle, and so on. So actually, here we have more than 50 design parameters. So this is 3 for the design parameters. So as I said in the previous slide, we have entrance section, middle body section, and run section. And these parameters represent the run section, and others represent middle and entrance sections. When you set these for about 54 parameters, you can generate a whole. So once we parameterize it, what we should do is, for our adjective-based design approach, we should learn the whole adjectives. We should learn the whole adjectives. So actually, we did a survey with more than 100 students in our faculty. So we show some yacht hull models to the users via a Google spreadsheet survey. So the question here is, which adjective can represent the yacht hull shown in below? So you should write here an adjective. So we have a list of adjectives such as strong, aesthetic, compact, and so on. So we did a survey with the students, and at the end, we checked the usage frequency for this whole adjective. So you see here, speedy adjective is used more than 100 times. Strong adjective is used about more than 80 times, and so on. So we just get 10 of these adjectives. So speedy, strong, aesthetic, aerodynamic, elegant, luxury, compact, classic, ordinary, comfortable, so, and charismatic. So we get these 10 adjectives, and then in the next steps, we studied on these 10 adjectives for our design framework. Okay, so what we should do is actually have design parameters. Design parameters are here. You see here the design tree. So we should relate or correlate our whole adjectives with design parameters. So to do this, we should again conduct a survey. So once we conduct a survey, we have a data. So by using this data, we can do deep learning. So here on the left side and on the right side, you see our survey. So what users should do is, they should choose one of the options according to the relation of the adjectives with the relevant model. So this is the same model, and then you see here we have a Likert scale. There's adjectives here: strong, speedy, aesthetic, usual, compact, and so on. So you should select one of these options. It's very poorly, neither well or very well expressed by the adjective strong, speedy, or aesthetic. Okay? So we got data from users, and then the next one is, before using this data, I would like to explain you how we generate this model. These are generated by us, but we cannot randomly generate. If we randomly generate, we cannot cover the design space. Therefore, we use Hakuji orthogonal array to generate 54 whole models that are used in the survey. But the problem here is, once we use the Hakuji orthogonal array, we have this kind of problematic holes. Okay, so to do this, we manually, to avoid this problem, we manually change the design parameters. So we convert this interesting hole, into more feasible one. Okay. So the next issue is to correlate our design parameters with whole adjectives like strong, speedy. So here we use Kolmogorov-Gabor polynomial to represent the correlation. So it is a polynomial representation. It's a nonlinear one. Here we have y. Here y represents our adjective. For example, in case of strong adjective, the value of y should be greater than 1.0. So here x represents my design parameter, a0, a1, a2, and these are the coefficients which are coming from our neural network.
Can I have a question?
Okay.
What is the full name of GMDH?
Group method handling for deep, just a minute, grouping method. I should check it. I'm not very sure, but it is G is for group, D is for maybe deep learning. But I may ask you, I may answer later, okay? This is a neural network approach.
I can find out from Google then.
Yeah. Let me just check it. Group methods of data handling.
Okay. Google is very good.
Yeah, we actually here we use one. There is a software. They have software as well. They have a non-commercial software. So for this analysis, we use GMD software. So we correlate using GMDH neural network. We correlate design parameters with whole adjectives. So we represent this correlation using nonlinear mathematical forms. So you see here, this is for strong. Y represents the strong value for a whole. So you see here alpha, R, RE, DR, BI, LM, beta, and so on. All of them are design parameters. Once you set these parameters, you can obtain a Y1 value. For example, in case of strong, Y1 value should be greater than, for example, 0.5. If your values, if the value you obtain is greater than 0.5, it means that your whole can be expressed by the adjective strong. So the next one is how can we use these complex nonlinear mathematical forms in generative design. For example, I would like to generate 5 strong wholes which are distinct from each other. Okay, this can be a generative design test case or generative design scenario. So remember that we have a formula, nonlinear formula in the previous page. So we can formulate this one as a constraint. Okay, so we can translate this one and then use this as a constraint in our previous generative design algorithm. Once you represent this guy as a geometric constraint and quantize it, you can use our particle tracing algorithm. So this formula is based on cost minimization. So once you generate some values here in different directions, you can find the minimized direction and you can move your particle in that direction. So to generate some adjective-based wholes, you use this formula. But the problem is, let's say I have a current whole form and I want to generate a strong whole. So what you should do is you have a set of parameters which should be modified to another set of parameters. So therefore, to modify this the whole using these parameters, we should have actually some shape operators. So we have another it's actually 2007. Sorry, we have another publications published in Ocean Engineering Journal. So we propose a parametric design approach, which is appropriate for our whole design framework. So we have elongation. So for example, we have a whole like this, and then we should elongate it. Now, by using just our elongation operator, we elongate, we have widening operator, deepening, modifying the entrance angle, and so on. So in this slide, you can see adjective-based wholes. You see here 2 aesthetic wholes, aggressive ones, comfortable ones, modern ones. You see here a value, 0.69. This is for the Y value. This is the value for this guy, the value of Y. So you can see the Y values here. So at the end, you can generate these adjective-based holes. So finally, we have a software which you can access through our website. We named as Modia. So here you can use the shape operators such as elongation or widening. Also, we have attribute modeling module. In this module, once you import a hole, you can automatically generate an adjective-based holes like this. Okay, the system automatically modifies the hole instead of you. Okay. All right. So for more details, you can check these two publications. Okay, another one is I'm going to explain generative design for the generation of car side silhouette. So here in this research, we develop a car side silhouette design system. So we concurrently consider stylistic form and aerodynamic performance. So if I ask you, for example, how do you buy a car? I'm sure you can say two things. The first one is I look at the appearance. The second thing is I look at the fuel efficiency, right? In Korea, maybe fuel is not very much expensive, but in Turkey, it's very expensive. Therefore, Turkish people mainly considers these two issues, stylistic form and fuel efficiency. So on the bottom, you can see a CFD test, computational fluid dynamics test. So by doing this, you can compute the direct coefficient of the car side silhouette. It's a flow capability or flow efficiency in the air of a car, of a silhouette. So here in this research, what we did was also silhouette. So we say silhouette this shape, okay? Actually, this is the side view of a car, So we also develop a silhouette direct coefficient prediction system. This is because actually CFD tests are very expensive. So just testing a silhouette took about 20 hours. Okay, 20 hours. So it takes too much. Therefore, we should have such prediction system. Let's talk about car side silhouette. The first step in car design begins with a simple two-dimensional car side silhouette sketches drawn by a car stylist. So this is the first step. Car stylist gets a pencil, and a paper, and he draws maybe hundreds of new silhouettes. Among them, they select a few of them, 2 or 3 of them, and then they can convert it into 3-dimensional one. So this is the basic design stage when for car stylists. Therefore, we focus on just this silhouette. So in generative design, once again, we should parameterize the model. A car side silhouette is represented using 9 characteristic lines. You see here we have front bumper line, grille line, hood line, windshield line, roof line, rear windshield line, trunk line, and rear bumper line. So we parameterize them using quadratic or cubic Bezier curves. So we can have different shapes. On the top, you can see different roof styles, windshield styles, grille styles, and bumper styles. And these X, you see here, X1, X2, we have X3, X4, X5, X6, and so on. These are our design parameters. Actually, these are the control points for the Bezier curves. So to predict the direct coefficient, we have 3 consecutive steps. The first one is the generation of silhouettes. Once we generate silhouettes, we call this step as silhouette sampling. We sample the silhouettes in the design space. This is a generative design algorithm. And then we test each of the sampled silhouettes using CFD. And then at the end, we use the machine learning step. We iterate these 3 steps until obtaining a reliable mathematical model. So these are 21 design parameters to represent the silhouette. T1, W1, or L3, T9, and so on. T represents the shape, L represents the length, and V represents the width for a characteristic line. So if you have a Bezier curve, let's say this is a hood line. If this is a hood line, let's say this is a Bezier curve, a characteristic line, it has a length and it has a width. So we respect these two parameters as a design parameter. So once again, we should form our design space. So to form the design space, we should set the design space boundary. So for all the characteristic lines, we set the lower and upper bounds. For example, the height of a bumper line should change between 220 millimeters to 450 millimeters. Okay, once you set these bounds, parameter bounds, we can have a design space so that you can perform generative design within the design space. So this is our approach. We should do first silhouette sampling. So for silhouette sampling, we have a NIF algorithm. So the objective here is to generate distinct silhouettes, different silhouettes as much as possible. So we want distinct silhouettes because if you just produce similar silhouettes, your CD prediction quality will be low. Therefore, distinctions is important. We use here the same formula, odds equals potential energy. We have two terms here, underline E and overline E. Underline E is to generate indistinct silhouettes, and overline E is for the generation of N silhouettes distinct from previously generated N silhouettes. Okay, so we check the similarity based on the position, slope, and curvatures at the points of the characteristic lines. So all these silhouettes are generated using our sampling algorithm. You can say a generative design technique. So in the first, we generate 100 silhouettes, and then we perform CFD tests here, and then we generate a mathematical model using machine learning techniques, and then we check our mathematical model whether it's reliable or not. If it is not reliable, once again, I generate 100 model. So this is the second 100 model. This is the third one, fourth one, and fifth one. So at the end of each sampling algorithm, we generate it and insert it into our silhouette database and generate a mathematical model using machine learning. And then finally, if it is not reliable, we generate one more 100 silhouettes. So actually in total, we generated 1,000 silhouettes. So each of these 1,000 silhouettes are tested via computational fluid dynamics tests so that we can compute drag coefficients. Actually, computation for a single silhouette takes about 20 hours. Let's say one day, actually computing the drag coefficients for 1,000 silhouettes took 1,000 hours, okay? It took about months, okay? More than 3 months. So once we have the data, we have 1,000 silhouettes with their design parameters, and we have computed drag coefficients, CD, we have CDs. So we perform two-step machine learning procedure. The first one is principal component analysis, and the other one is regression. So at the end, we have principal components here, each of which are represented using design parameters such as X3, X51, X4, and so on. So each of these principal components are placed in the equation. Once you place them in the equation, you can have the drag coefficient values. So it's very simple. In order if you use this empirical equation, it takes less than 0.1 seconds. It's milliseconds to compute the drag coefficients. Otherwise, you should test using computers CFD analysis, which takes about 1 day. Okay, so this simplifies our job. If you have such kind of empirical formula in design optimization, you have a very big advantage, because in a short time we can define thousands of new designs. So this is our CD prediction system convergence criteria. So we have, first of all, we generate we sample 100 silhouettes, and then our average CD error is about 13%. When it becomes 200, our CD error becomes more than 14%. So we still generate these silhouettes, and at the end, after 800 silhouettes, the error was less than 10%, so that we convert our system. So these are some generative design test cases. So this is a typical scenario. I want to design 20 distinct silhouettes whose directs are less than 0.3. So these are distinct silhouettes. So we use also Eclipse potential energy, and then we add this constraint, directs smaller than 0.3 in the problem. So we have 20 silhouettes. Similarly, we want to generate 3 silhouettes with drags smaller than 0.22. On the top you can see the silhouettes. Another one is between 0.33 and 0.35. These are another silhouettes, and then we generate the silhouettes greater than 0.45. Actually, in this design case, we tried 43,700 silhouettes are investigated in a short time. Maybe it took about just 2 minutes to investigate all these silhouettes. Otherwise, you should wait about months. Okay, so you can see our system. You can see our system. We call them as IP. So this is a car site silhouette recommender system. Once you modify this shape, the silhouettes using sliders, you can see the fuel efficiency rate, and you can see the drag coefficient. These are the predicted ones, actually, predicted values, so which are computed using the mathematical formula here. Okay, this formula is computed, computes this drag coefficient. And I'm going to conclude my talk, and these are the final remarks. So actually, generative design is an open issue in computer-aided design and is expected to open new doors in the CAD field. Large number of designs can be scanned in the design space via generative design, some of which may not be considered by designers. Basic steps of GD are, once again, model parameterization, fitting the design space, and using an appropriate GD algorithm for synthesizing new shapes. Okay, thank you for your attention.
Thank you.
So I can maybe get questions if you have.
Yeah, I hope there are many.
Actually, this is somewhat, there are some good mathematics beyond generative design, actually. But the big advantage is, maybe I can just open this slide. So it gives you very good opportunity to design new models in a short
time. I have a question.
Okay.
Can strength testing be included like the CFD testing? Like in case of rim, it has to be tested via FEM, whether it is good over the life cycle or not, or something.
Actually, it's very difficult to understand the question. Can you once again repeat?
What question is? how can we incorporate FEM?
How can we calculate?
Calculate or incorporate.
Incorporate. I don't understand. What? Yeah.
Include.
Okay, include.
Finite element analysis.
So you're asking to include something, but I don't understand. Including
finite element method.
Okay. Okay. How can we include finite element method in case of wheel rim? You see? Okay. So actually, in this case, we haven't included FEM in wheel rim case, but I think you are talking about this slide. This is just for illustration. This is just for illustration. Actually, in generative design, you can include finite element in two ways. The first one is you can integrate your CAE software to your generative design software. This is first way, but this is very costly. It has a high computational cost. Therefore, what you should do is you should simplify this simulation in FEM. If you simplify it, you can simulate it in a short time. For example, the real simulation takes about 3 hours, let's say. It takes about 3 hours. If you simplify your simulation, it may take about less than 5 seconds, so that you can try different options. So the first one is you can simplify. Another one is you can do machine learning. So in machine learning, you can try many options about wheel rim FEE simulation. Let's say you try 1,000 or 100, you do tests, and then you have a training data. By using this training data, you can obtain mathematical model so that you can predict the stresses on the wheel rim.
Yeah, Professor, I have a question. You said the designer should decide parameter for CAD manually, right?
Yeah. Yes.
Cool. My question is, can we use the machine learning or deep learning to decide parameter?
Oh, it's actually very good point. Someone can do it, but I haven't seen anybody to do this job. Actually, but if you want to apply machine learning to design or to determine the important parameters in a model, what you should do is you should establish a training data. Data. This training data, maybe you can ask users to take important portions or important parameters in the model. So you can show the CAD model to the designers or to the users, and the users can take or can select important parameters on the model so that you can do some machine learning. But maybe there can be some more sophisticated techniques can be used, but still I'm not sure about how to apply these techniques for your problem.
Okay, thanks.
Here we just use designer's parameter, but in the literature there are some works they use just mesh model, for example, or they use just V-spline surface model. So if you use V-spline surface model or mesh model, you are going to have many geometry parameters. For example, 1,000 geometry parameters. Actually, this is not very desirable. Why? Because in machine learning, if you have lots of parameters to handle, it's very hard to handle, or it's very hard to obtain a reliable mathematical form. Therefore, they use principal component analysis to decrease the number of parameters, actually.
Thanks.
Yeah.
Professor, I have two questions.
Okay.
First, regarding parameterization. You showed us a parameterization tree.
Okay.
Is that how it like there were different sections in the ship?
Just a minute. I'm gonna open. Where did that? Here. Okay.
Yeah.
Yeah.
Yes. So there are 3 different sections in the ship.
Yes.
Can be more depending on our model. So is there a chance that there is any redundant parameter or 2 related parameters?
Yeah, I see. I see. Actually, in machine learning step, you should avoid redundant parameters.
Yes.
Your point is true. So actually, here we obtain these parameters manually. So we visually inspect the whole using these parameters. So actually, there are not too much redundant parameters here. For example, the first parameter is length for entrance. Another parameter is for length for middle body, and another one is for run section. So if you have these lengths, and if you have an overall length will be redundant with these parameters, right? With these length parameters. So actually, we don't have redundant parameters, I think.
My second question is regarding the 2 softwares which you showed us.
Which one?
First one, let's say for the yacht.
This one, you mean?
Your lab software.
Yeah. Okay. I see. This one or other one, Modia?
The first one. Yeah.
This one. Okay.
So, Professor, are you using some libraries?
Actually, we use Parasolid libraries. So
Okay.
Parasolid libraries to develop this one. This is based on B-spline curves and Kunz patches. Therefore, we mainly use these class libraries while developing shape operators and attribute-based modeling. So if you wanna download this software in our website, there's a software section. So here you can go behind, you can get the exe file from here. So, and then there are manuals here so that you can install it to your PC.
Okay. Thank you very much, Professor.
Yeah, my pleasure. So if you don't have questions, I think it's okay.
Right? 10 more minutes. No idea. Then you can ask about Istanbul.
Okay.
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 Do you have an international school?
Sorry?
International student.
Yes, we have international students. Actually, this software is developed by a guy who is from Pakistan.
Pakistan.
You know him, Shahroz, I think, Professor. This guy.
Oh.
When you were in Kayıp, you met Shahroz and Kemal. You remember?
Ah. Your friend. Huh? I don't know.
What was his undergrad university? Did he completed his bachelor's from Pakistan?
Actually, this software was developed by my master student who is from Pakistan, actually.
The question is, the student from Pakistan, has he got his bachelor degree from Pakistan?
Yes, yes. He got his degree from Pakistan. He did his master's here, and then right now he's in University of Strachel in UK, United Kingdom.
His question was which university in Pakistan?
I'm not sure actually. Maybe you can just check.
Yes.
I'm not sure about which university he's from. Yeah.
Okay. Since we don't have a question, then we can close earlier. Right?
Yeah.
Okay. Thank you very much.
Yeah, it's my pleasure. Thank you very much. So hope everything will go well for all students.
I found that your university is very old.
Very old, yeah.
Very old.
Very old, yes.
250 years.
About 250 years, yes.
What was the first university in the world?
It is 1453. When Turkish people got Istanbul, they directly established a university. In 1453, it's Istanbul University. 1453, yeah.
300 years more.
Yeah.
All right. Yeah.
Okay, thank you, Professor.
Bye-bye.
Okay, bye-bye.
Bye.
You can leave the meeting.
Okay, so I need to click something.
You don't need or
Back to meeting, or no? Stop share, no.
And the bottom of the right side, end the meeting.
Leave meeting. I see. Okay, see you. Yeah.
Bye. Bye.
Thank you.